Okay, what if you could create these tiny, microscopic cleanup crews to go after our absolute worst pollution? And then, get this, what if, to make sure they don't get out of hand, you gave them a self-destruct button? Well, today, we're diving deep into the world of suicidal supermicrobes and their incredible built-in kill switch.
Let's just start with a simple, kind of scary fact. There are man-made chemicals out there, right now, soaking into our planet that just don't break down. They're designed to last, and they do. They just stick around, creating this massive long-term headache that we've got to figure out how to solve.
So here's our game plan for this explainer. First, we're going to unpack that pollution problem. Then, we'll look at how scientists are actually engineering a solution. But that, of course, leads to a huge question, kind of like opening Pandora's box, which, luckily, is answered by a really clever innovation, the kill switch. And finally, we'll wrap up by looking at what this all means for the future.
All right, let's jump right into part one, the pollution problem itself. We're talking about chemicals that are so stubborn, so persistent, that nature just throws its hands up.
Now, the scientific term for these things is recalcitrant, which is really just a fancy way of saying they refuse to break down. A lot of them are what we call xenobiotics, compounds with these bizarre chemical bonds that natural microbes they don't know what to do with them. We're talking about some really nasty stuff here like PCBs, PAHs, and some heavy-duty pesticides. And the critical thing to remember is they're not just sitting there. They pose a very real toxic threat to wildlife, to ecosystems, and yeah, eventually to us.
So how in the world do you fight a problem like that, a complex chemical problem? Well, it turns out the most exciting answer is a biological one. Let's get into how that actually works.
The whole idea is built on this concept called bioremediation. And at its heart, it's super simple. It's about using microorganisms, bacteria mostly, to do what they do best. Eat stuff and break it down. We're essentially finding nature's own little cleanup crew and putting them to work on our biggest messes.
But okay, what if nature's crew isn't quite up to the task? That's where things get really cool. We're talking about genetically engineered microorganisms, or GEMs for short. Using something called recombinant DNA technology, scientists can basically give these microbes a software update, a new set of genetic instructions that teaches them how to devour those super tough pollutants they couldn't even touch before.
And make no mistake, this isn't just guesswork. This is incredibly precise work. Scientists can use techniques like rational design to literally build new metabolic pathways from scratch. It's like being a molecular engineer, piecing together the biological machinery that will let a microbe eat, say, a PCB for lunch.
You know, this isn't some far-off futuristic concept either. People have been working on this for decades. In fact, think about this. All the way back in 1996, the U.S. Environmental Protection Agency gave the green light for the very first field test of GEMs for bioremediation. But taking that first step, well, it raised a massive question. And yeah, that first step immediately opened up what you might call a Pandora's box. It forced everyone to ask a huge and honestly pretty scary question. Once you release these super microbes out into the world to do a job, what happens to them after the job is done?
I mean, it sounds like the perfect solution, doesn't it? We custom build a microbe to eat our pollution. Problem solved. So, what's the catch? Come on, you know there's got to be a catch, right?
And here it is. This is the big one. This is the central risk. Once the pollutant they were designed to eat is all gone, what's to stop these highly specialized, lab-created organisms from just sticking around forever? Could they disrupt the natural balance? It's a question you absolutely have to answer before you go any further.
Which brings us to, without a doubt, the most fascinating part of this whole story, the solution. An incredibly elegant answer to that very complex and very serious risk.
What's so important here is that the scientific community took this risk seriously. They didn't just ignore it. They knew that to use this technology responsibly, they had to build a foolproof safety feature right into the organism's DNA from the very beginning.
And you can see that thinking right here in the research. This quote says it all. The potential risks originated the necessity to construct systems by which bacteria are killed in a controlled suicide process. In other words, the kill switch wasn't an add-on. It was a foundational piece of the design from day one.
And that line of thinking led us to the hero of our story, the suicidal gem, or S-gem for short. This is the next evolution. It's a microbe that has not only been given the tools to eat pollution, but also a very specific, pre-programmed instruction to self-destruct once its mission is complete.
So, the mission profile for one of these things is just beautifully simple.
Step 1, you deploy the SGEMs at a contaminated site. Step 2, they get to work and clean the area by chowing down on the pollutant. Step 3, and this is the genius part, the kill switch is often tied to their food source. When the pollutant is gone, the containment system activates and they self-destruct. And the final result, step 4, is a safe, clean environment. The tool does its job and then just neatly removes itself from the picture.
Okay, so let's zoom out and just look at the big picture here. This technology is a massive leap forward, and with it comes both incredible promise and, of course, some serious responsibility.
This comparison really lays it all out perfectly. You've got your natural microbes. They're safe, but they're slow and can't handle the tough stuff. Then you have standard GEMs, way more powerful, but they come with that big environmental risk. But then you get to SGEMs. They give you the best of both worlds. All the enhanced power of genetic engineering, plus that absolutely critical safety feature of being designed for removal. It's fast, it's targeted, and it's contained.
So, the technology is here. We have powerful, precise, self-contained cleanup crews that literally disappear when their work is done. It is a genuine game changer for some of our most toxic, stubborn pollution problems. Which really leaves us with the million-dollar question. The science works, but are we, as a society, ready to deploy these little guys at a massive scale? That's something we're all going to have to think about.